All right, our second lecture on capacitance and capacitors. So, before we talked about the idea of capacitance, which we defined to be this proportionality between how much charge can be stored on a conducting surface. So we have some conducting surface here and here, and we had a little demon that kept stealing electrons and throwing them on the other conductor to create a positive net charge here and a negative net charge on this side. And in doing so, they created an electric field in the process between the two that, unless there is some way for those charges to get back to one another, that electric field then becomes essentially permanent until the charges change or move or do something. So there's energy, and that energy, you can't just create an electric field from nothing. Work had to be done in order to create that electric field, and so in a sense, the electric field is storing energy between these two conducting plates or surfaces. So we define capacitance as the proportionality between how much charge is built up on each plate compared to the potential difference that exists between the two plates. And again, since potential difference connects to electric fields, that's saying something about the charge that's being built up and then the energy that's being stored in this electric field. We worked out exactly how much energy is being stored or it takes to make this thing. So in a sense, by conservation, you can think of it as energy you can then get back if you were to tap out and cash out. And it turned out that the total potential energy that's stored in this capacitor is 1/2 times the capacitance times the potential difference squared. Kind of looks like kinetic energy, which is kind of nice. Easier to remember. And another quantity that is useful is to talk about the energy volume, or energy density rather, or energy volume density is really what I should say. The total amount of energy per volume. And I say that because if you look up like energy density of batteries, and if you look up Tesla's most recent battery, what's its energy density, it will often tell you kind of energy per kilogram. So that would be what I might call a mass density. But this is a volume density, total energy per volume. And then it worked out for, in the case of the parallel plates, we were able to derive that this has the expression 1/2 epsilon naught E squared. But then I mentioned that that's actually a general result. So all of these on top are completely general. And again, this kind of volume density does nicely show that there is a connection between the amount of energy that's stored in a volume and the electric field itself. And then particularly, we work out for parallel plates, so two plates that are separated by some distance d and have area A. The potential difference between the two plates is related to the electric field by this formula that we've seen many times already. And we use this in combination with this to derive that the capacitance of parallel plates is epsilon naught, the area of the plate divided by the separation distance. So this idea of capacitance is connecting to the amount of energy that is able to be stored between these two conducting surfaces. And so now, without a demon, how really do we do this? That's what we want to talk about first. And then I want to talk about what happens when you try to connect capacitors in series and parallel. And then I want to talk about, actually I do want to talk about the Tesla battery and kind of current innovations and what we're thinking about in terms of trying to get the energy density of electric batteries as high as they can be. So, how do we actually do this? So suppose you have two conductors that are initially neutral. Conductors, remember, are equipotential surfaces. So everywhere on and in the conductor is at the same value of potential. And if I don't have a demon that can come take electrons from one and place them on the other, how do I get this charge separation to occur? You might think, because it's not going to occur naturally. There might be, even if there is some leakage current, there's not the current, charges are not going to naturally want to fly from one to the other. The electrons want to hang out where all the nuclei are. They don't want to separate from the nuclei and then fly away unless they're compelled to. So I think, well, what if I connect them by a wire? So a wire, which again we will also assume is a conductor. Well, if I have a conductor touching a conductor touching a conductor, I'll use color in this lecture to specify equipotential surfaces. So if this entire conductor on the left, since it is a conductor, if it's an equipotential surface, then by touching a wire to it, that makes the wire an equipotential surface at the same value of the potential. But then since it's touching this conductor, this is also then the same potential in this entire thing. When connected by a wire, is a big ol' equipotential surface. The whole thing is an equipotential. Now, for equipotentials, that means charges can move along equipotentials without any work being done on them. But again, then that means that there really is no energy that's being built up. One, the electrons are not going to want to just naturally flow to one side and leave all the positives on the other, because with an equipotential surface, they could just easily flow right back for free. They don't have to fight against an electric field or anything like that in order to get back to the positive charges. So they're not going to naturally want to separate. So if there's no delta V, then there's no reason why they would separate naturally. So that wouldn't work. So this won't create any sort of charge separation. On its own. So again, it does seem like we need some sort of demon. And I joked at the end of the last lecture that you could go to the store and buy a can of demons. But it might be called a battery when you get to the store. So if I have the two conductors, and I have some sort of battery here. I think it's a 9-volt battery. I'll talk about what that means in a second. And I connect one terminal to one conductor and another terminal to another. So the battery attempts to hold a particular delta V across its terminal. Across its terminals. So in the case of a 9-volt battery, the positive end is at a potential that is 9 volts higher than the bottom. So you might take the top to be 9, the bottom to be 0. And those are two, and the terminals are two conductors. So by connecting the top terminal via a wire, that creates an equipotential surface along the wire. And then since it touches this conductor, that conductor then is held at the same potential. We'll call it 9 volts. Similarly for the bottom, the wire then, and then this conductor, get held at that potential. So in this case, the battery does establish a potential difference across the two conductors. Or I should say, the battery will work to establish a potential difference. It doesn't just happen automatically. The battery will work to establish a potential difference across the conductors. And particularly, if 9 volts, if we call that the potential of the battery, again, knowing that really what we're talking about is a potential difference, then if you just look at the colors, the battery will aim to establish the same potential difference across the two conductors, such that the blue conductor will be 9 volts higher than the red conductor. And it does so by acting as a sort of charge pump that pumps, in the conventional case, positive charges from the negative terminal to the positive terminal. That, in end, drives a buildup of positive charges on one conductor, and then through deficit, builds up negative charges on the other. And then, lo and behold, you have the same sort of setup that we had before, where an electric field can then be established. And you have effectively charged this capacitor, such that if you were to then disconnect the battery from the capacitor, copy this. If I were to then effectively disconnect the battery from the capacitor, there is positive and negative charges that are pulling towards one another, so they feel compelled to get as close to one another as possible. And notice that then this kind of configuration is maintained, so that once battery is disconnected, the capacitor remains charged. At whatever potential it ultimately reached. If it's fully charged, in this case, it would have established the same potential difference as the battery. And we can actually work out the time dependence for a simple capacitor connected to a battery once we get a little bit farther along in circuits. We will solve that differential equation and get the amount of charge build up as a function of time, or the potential difference as a function of time. So now we have to make some definitions and notice particular conventions. So if we go back up to the one where it's connected to the battery, the idea of the battery acting like a charge pump, it appears like I'm trying to say that positive charge is kind of driven upwards. So you might imagine that there's some sort of motion of charge in that direction. This is the direction that we define as the conventional current. So we have conventional current where we say that the motion of charges, or current, is the motion of positive charges. Now in reality, again, thanks Ben Franklin, in reality, it's not positive charges that are moving, but electrons that are moving in the opposite direction. So most textbooks will do all of this in terms of the definition of conventional current, but when you're looking at, say, an engineer manual, you have to make sure and see whether or not they're specifying that things are being drawn in terms of conventional current or actual current, which again are it's actually electrons, not positive charges, moving in the opposite direction. The good news is that this is mathematically equivalent for 99% of the time, percent of all cases we'll be considering. Mathematically equivalent most of the time. In that positives going in one direction gives you the same answers as if you had negative charges, which you might assume would involve a minus sign, moving in the opposite direction, which would involve another minus sign, and then they cancel out. So this is mathematically equivalent most of the time. There are some exceptions that we will experience, for example, when we get to magnetism, where you actually can tell whether it's one or the other based on calculations you can do related to magnetic fields. So that's one definition. And I will stick with the conventional current definition, as does your book. So a battery, we'll be getting more into current in the next couple lectures. But for a battery, we can think of this, I called it a charge pump. And I think that works for us for right now. Because there's a lot of misconceptions over kind of what is a battery doing, and is it driving energy, or is it driving charge, or is it creating electric fields? And we're going to make some simplifying assumptions as we try to model this and get some intuition about this. But I've been really enjoying kind of just watching YouTube videos and learning a lot from electrical engineers about what actually is going on in currents and circuits. But for us, we can think of this kind of like a charge pump, where and it's pumping from the negative end of the terminal to the positive end of the terminal, which again, if you remember with potentials, right? Potential going from positive to negative is the direction of the electric field. If you think of there being a little electric field inside the battery. So the battery has a little electric field that points from top to bottom. So a positive charge naturally left on its own wants to go from top to bottom. But if I have a pump that pushes it against that desired direction, then in a sense I'm increasing the potential energy that it could then go off and do work elsewhere, and that energy can then be turned into something meaningful. So the analogy in this case or the analogy that we can use is an actual water pump. So if I have two reservoirs, cylindrical things that hold water, and there is some sort of pump between them, and they're initially both filled about halfway full. So they're both filled halfway. That would be a very natural state. If you look at the buoyancy fluid dynamics chapters of their book, they would maintain themselves without us having to do anything. But if I have a pump that tries to push water from the right reservoir to the left reservoir, that of course requires some work to be done. That doesn't just happen for free. And so you can imagine in this case, then after the pump does some work, you might have more water filling up this reservoir with less filling up this reservoir. Color it in. Clearly this is important to our understanding. I have this colored in blue. There is some difference between or work was done that then has helped fill up the left reservoir compared to the right reservoir. And there is a limit to what this pump can actually do, right? The pump, has some sort of motor that, can continuously try to pump water, and it can't, and if it's actually filling these two reservoirs and it's not just pumping water from out of one container and then it's just flowing, down a hill or something like that, this pump can only push so much water into the left reservoir, because as the left reservoir fills up and up and up, there is a back pressure that all that water is pushing itself back down from gravity in this case. That if I were to turn the pump off, it makes sense that they would then reach the left reservoir would try to empty out back into the right reservoir, and they would reach some sort of equilibrium again. So to maintain that difference, the pump is continuously working to push water into the left reservoir, but then the back pressure of that big tower of water that's crushing down on the pump, there is some limit to how much the pump can actually push. So there's some limit based on this kind of delta H, right? There's this height disparity that's been created. That the pump there's some limit to where that's some mechanical limit of what that pump can do in this case. So the water pump has, in a sense, limits, and you can think that since this is really based on gravitational potential energy, right, that there's some limit that might be connected to this delta H that it can establish. This also is very similar for batteries. So for batteries, it is pumping charge in order to maintain some particular potential difference. But again, how does the battery know when to stop pumping? In the case of this capacitor, right? If it were connected to a circuit, it might try to do it just continuously. But in the case of this capacitor, if we go back up to the picture, right, you can imagine that as it starts and there's no charge on these plates, and it pumps a little bit of charge, so you get one of these pluses and one of these minuses. That creates a potential difference that's not 9 volts on the right-hand side. And then it pumps some more charge, and it takes a little bit more effort to do it that time because it's trying to push a plus charge over here, but then there's already a plus charge that's resisting that charge from coming over. But it can pump those over, and then there's 2. Then it might try to send another one over, and it's getting really hard at this point. Then it might succeed at sending another one over, and then there's 4. But then try as it may, there's this back pressure that is pushing back on the battery that it can't really push any more charge in that direction because all that positive charge that's built up is repelling the inclusion of another positive charge. And so there's, again, a limitation that occurs. So the batteries have limits. That's related to some sort of delta V, you can imagine. And so that's why you see, that, again, the idea of adding more charge to one of the plates would produce a back reaction that would push that charge back away. That's why then when you see kind of the rating on the side of a battery, it's telling you the kind of potential difference that it can effectively establish. 1.5 volts for a kind of AAA battery, 3.7 for lithium ion, or 9 volts for a 9-volt battery. That's really what that means. It's the potential difference it can effectively establish. Okay, so before I move on to the next page, despite my beautiful drawings of capacitors and batteries, there are simple electrical engineering symbols that are used as conventional ways of drawing batteries, capacitors, wires. And so we'll start to use those as well. For a battery, kind of the original batteries used to be stacks of plates, plates stacked on top of one another of different metals that would allow for electrons and ions to kind of establish this delta V that was necessary. They usually were submerged in chemicals and whatnot. So the battery symbol is, again, a stack of 2 plates. But since they're different plates, we write them at different lengths with the idea that the long side is the plus and the smaller side is the bottom. So we'll use that for batteries. Wires will just be a straight line. And we will assume that there is no We haven't defined what resistance is yet, but we will assume that wires are perfect conductors, or that there's no internal resistance within the wire. And then capacitors, since parallel plate, as I said last time, is typically the most common. It's usually drawn very similar to a battery, but as two equal length plates, as two parallel plates. The other common ones are kind of spherical capacitors and cylindrical capacitors, which we are going to, well, this is the second video. Presumably, we have already worked out using Gauss's law in class what the capacitance of those are as well. All right, so maybe that's worth a highlight, right? Because this is good too. We will see this again. A nice page, lots of nice color. All right, so now, scroll down my notes. So now if I want to then represent my battery, and it's connected to, now I'll start using parallel plates, a parallel plate capacitor. That can then be represented as the battery, and it's connected to two parallel plates as such. So, again, we've talked about how the idea is that this battery will pump charge until it establishes some potential difference across the capacitor plates. So again, if I want to draw equipotentials as colors, the positive terminal of the battery then establishes this as an equipotential surface. Notice it's only the top plate. And then the negative terminal of the battery establishes the bottom as an equipotential surface. Such that in going from positive to negative on the battery, that's some potential difference V battery. And again, by looking at the colors, there's some similar potential difference across the capacitors, going from positive to negative. The same, 9 volts or 1.5 volts, what have you. So, just as a quick example, since I know the charge that's built up on the capacitor is equal to the capacitance times the potential across the plates. If I have a capacitor that is 10 microfarads with capacitance and is connected to a 1.5 volt battery, once it is fully charged, the charge that is built up then looks like it is just 10 to the minus 5 farads, the SI unit for capacitance, times 1.5 volts, SI unit for voltage or potential difference. So then that looks like it's just 1.5 times 10 to the negative 5 coulombs. If they work in all in SI units, I know they will work out at the end of the day. And again, remember we defined a farad as a coulomb per volt. And also remembering that the C for coulomb is not the C for capacitance, which is why I try to put the little serif on capacitance. Okay, pretty simple example. A battery connected to a single capacitor. So now imagine the following. I have some battery which I will hook up to this box that I have. I have this big old box that I bought from the store. And there's an in terminal and there's an out terminal. So I connect the battery to this big old box. And on the box is the equivalency brand box. So the company is named Equivalency. So it's an equivalency brand box where they claim inside the box is a single capacitor with capacitance C subscript EQ. So they claim inside that box is a single capacitor that has a capacitance of C sub EQ. And so they have kind of their logo, in this case, is just a single capacitor that's hooked up. And they claim the capacitance is C sub EQ. So then I know, and then I test to ensure that when I hook this box up to my battery, there's a potential difference from positive to negative V battery that indeed, and I can test this with my digital multimeter that you've used in lab, I can establish that there is the same potential difference that's built up across the box, as I would expect once it is fully charged. And given the value of C equivalent, I could then calculate the amount of charge that's been built up. However, you then open the box and discover the following. You have a battery that goes into the box and comes out of the box. But in fact, what's going on is it goes into the box and it goes into one capacitor, and that capacitor goes out and goes into a second capacitor, which then eventually leaves the box. I had to take a phone call. So in this case now we have a battery that is hooked up to two capacitors, we say, that are hooked up in series. And they don't necessarily have to be identical capacitors. They could have different capacitance for each. But the idea is that when the box was closed, we said above that there's a relationship between the charge that's being built up, this equivalent capacitance, and the potential difference across the box. Particularly the potential difference across the box better be the potential across the battery. And then when we open the box to reveal that actually it was two capacitors connected together, we still need to get a consistent result. So the idea here is that if we were to take two capacitors in series, what is the equivalent capacitor that if I were to take the two out and replace it with a single capacitor, what should that single capacitor be that would give me the same overall answer from one end of the box to the other end of the box? So this is the idea of equivalent capacitors, or equivalency between capacitors. And then when we get into circuits, we'll do the similar thing with resistors. So I'm going to erase, just to make this not too busy, I'm going to erase the box. And then I could ask myself, well, I have my battery, so I know charge is going to want to flow in that direction. And then charge is going to build up on this side of this particular capacitor. And that negative charge is going to build up on this side of that capacitor. But then these negative charges are going to pull positive charges down from the top, so that a positive is going to form here, and then similarly a negative is going to form there. So I do expect that this thing could charge up similarly. But now we have to think about what's the same and what's different in the cases where there's two connected together versus just one. So let's first look at equipotential surfaces. Let's say I used blue for coming out of the top of the battery. So coming out of the top of the battery, it's connected to a conducting wire. That means that part there in blue is all at the same potential. Similarly, the negative terminal of the battery establishes that this part is all at the same potential. And now there's this third region, which, since this plate and then the top plate of the second capacitor are all touching one another via a wire. That is all at the same potential. So I might want to specify that there's some potential associated with the battery, or a potential difference across the battery. There's some potential difference across capacitor 1, and there's some potential difference across capacitor 2. And then these capacitors need not be the same. So let's say that the first capacitor has capacitance C1, and that this capacitor has some capacitance C2. Some charge is then pumped from the battery down towards capacitor 1. So let's see, what can I do? I can't use B for blue because I already have B for battery. Well, actually, let me change this. Instead of V sub B for V battery, let me actually just write V bat. In this case, it looks like we're saying that V battery, which is a potential difference, looks like, and again, that means that some, if it's 1.5 volts, you can think of blue as corresponding to 1.5, red corresponding to 0, for example. So it looks like this is whatever the value is of blue minus whatever the value is for red. And then when I look at the potential difference across the first capacitor, the positive end is blue, the negative end is yellow-green. So I know then the potential difference across the first capacitor is going to be blue minus this kind of yellow-green. And then the potential difference across the second capacitor looks like it's going to be yellow-green minus whatever the potential is corresponding to the red color, red. Right, that would then specify the actual values of all of these. So one thing we can notice is that the voltages, for capacitors in series simply add. And we can see this by let me actually, so I don't have to keep switching over to highlighters. Let me call this, if I want to assign values, right, let me see, this is V blue, V red, V blue minus V green minus V red. So then notice that if I take the two voltages for the capacitors and add them together, V1 plus V2, that seems like it's just V blue minus V green plus V green minus V red, or V blue minus V red, which seems like it's the same thing as V battery. And this might not seem too surprising because this also matches what we said has to happen. We said that the voltage, the potential across the battery was some V battery. And so if this were a single capacitor, we know that going across the box, that the potential difference must also be V battery. So in going from the top of the box, which we might say is here, and then the bottom of the box here, it does seem like the potential difference matched what is going on with the battery, as is to be expected. So we have voltages for capacitors in series simply seem to add together. This actually is the same idea with batteries. When you have a remote control or something like that that has a battery, maybe there's a AAA here, so this is 1.5 volts, and then you have to put the negative terminal and the positive terminal in the same orientation, and this is also 1.5 volts, that those together then create a potential difference of 3 volts. Because you get a kind of positive to negative, there's 1.5 and then another positive to negative, another 1.5 across the terminal on the right and the terminal on the left. So that the delta V, they just add together. Also makes sense why if you put one of them out of order, it doesn't work, because essentially then they cancel the potential differences cancel each other out. So voltages for capacitors seem to add in series, and then we need to think about such that, okay, so then if I write this down, simplify, right, it says that V battery equals V of capacitor 1 plus V of capacitor 2. Which, yeah, so then the next thing to point out is, again, the idea is I want to come up with some sort of connection between these two individual capacitances and the single capacitance that I thought, right, was supposed to be the capacitance for the entire box. That it goes in and comes out, and there's a single capacitance that corresponds to the box. And there should be then for a connection between this equivalent capacitance and these capacitances. So in the case of the box, we said that across the box, there's a single capacitor and there's the potential difference of V battery. Such that for the box, I'll go back up here to the drawing. Actually, I drew it right here, right? For the box, we have this relationship. That the charge built up, across one end of the box compared to the other is equal to this equivalent capacitance times, in this case, the voltage of the battery, V sub B. So I could then write this as, for the box, that V battery is equal to Q over C equivalent. And this is kind of the Q across the box. So I'll write that here such that then I can write this. If this is Q across the box divided by C equivalent. And then that is presumably connected to the charge that builds up on capacitor 1 divided by its capacitance, and the charge that builds up on capacitor 2 divided by its capacitance. Okay, so we're getting closer. I can see now we have one equation that has all three capacitances in it, but I still got all these Q's that I don't quite know how to figure out. But if we think about this, there's actually a very simple relationship between all these charges Q. That if you think of the battery drives some charge forward, and then that builds up on the top plate of the first capacitor. It makes sense that as the charge builds up, it then pulls an equivalent amount of charge from this side of that capacitor through the battery. So I at least know that if there's two pluses on the top, there should be two minuses on the bottom. And then again, it's not too hard to then argue that there should be an equivalent amount of charge that builds up on the opposite sides of the capacitor. That's how we were defining the capacitance. If there was more or less, there were, say, only one negative sign here, but two positive signs over here, seems like there'd be a net desire to pull some more negative charge up. So if there are two pluses here, it makes sense that then two negatives form here, which then make two pluses form here, which then match the two minuses that were down here. So the amount of charge that builds up across each capacitor is the same. And it must be the same as the amount of charge that was driven through the battery. So then we have also for capacitors in series, that the charge on each capacitor is the same. For that Q bat equals Q1 equals Q2 in this case. And therefore, if all these Q's are the same, I can then cancel them out, and I get the expression 1 over C equivalent equals 1 over C1 plus 1 over C2. And these are for capacitors in series. Which is worth a highlight. Then I can take two capacitors and take them out of the circuit and replace them with a single capacitor, which, if it has a capacitance equal to this C equivalent, gives me the exact same result. Essentially, what the battery assumes is connected to it is this single capacitor with a capacitance of C equivalent. And if in actuality, when you zoom in or open the box, that one capacitor is actually two capacitors connected together, this is the relationship between what the battery sees, in a sense, which is a single capacitor with capacitance C equivalent, versus what is actually there, two capacitors in series. And I will also note that this generalizes that if there are, say, 3 or 4 or 10 capacitors in series, you just add up more terms. Right? It's just 1 over C sub I, and you just have as many of them as there are. So let's do an example, plug in some numbers with this one. Suppose I have a battery, and then it goes up here and connects to one capacitor, and goes down here, connects to another capacitor, and goes over here, connects to a third capacitor, and then goes back to the battery. This C1 is 10 microfarads. C2 is also 10 microfarads. Then C3 is, say, 100 microfarads. And we are connected to, say, a 9-volt battery. What is the equivalent resistance of this circuit? If the battery sees itself connected to a capacitor, what is the equivalent capacitance of that single capacitor that it would see? All right. And we have to use, right, there's formulas, of course, we could use, but then we should always be thinking conceptually what's going on. And again, in terms of equipotential surfaces, we have this is an equipotential surface, this is an equipotential surface, this is an equipotential surface, and this is an equipotential surface. Each of those capacitors, since the battery kind of pushes a charge Q forward, there's some Q that builds up here, and then some negative Q builds up there. So then some positive Q builds up there, some negative Q builds up there, which then some positive Q builds up there, some negative Q builds up there. Capacitors in series share the same charge. Or rather, they have the same charge built up in each. Okay? So, the first step I might be, we can prove this formula first if we want, or we can do it in steps, of course. So I know that I have this. Draw on all the other one, redraw. This is capacitor 1, 2, and 3. I know that I could replace the first two capacitors. So I know I could replace these two together with some equivalent capacitance. and the third one's still there. So this is still capacitor 3. But then this is capacitor, I'll say capacitor sub 1, 2. That's the equivalent capacitance of the first two, such that 1 over capacitance 1, 2 is equal to 1 over capacitance 1 plus 1 over capacitance 2. Now, the usual pitfall that students make mistakes when doing this is they will evaluate the right-hand side, but then forget to take the inverse of it at the end of the day. Because if I just plug in numbers to the right-hand side, that does not give me C12. That gives me 1 over C12. So then I have to flip the number at the end. So since C12 and since C sub 1 and C sub 2 are both 10 microfarads, this is then just 2 over C sub 1, and that's equal to 1 over C sub 1, 2. So then if I flip both sides, then C12 equals C1 divided by 2. So then if this is 10 microfarads, so this then is C12 is equal to 10 microfarads divided by 2. That looks like it then just becomes 5 microfarads. So the equivalent capacitance of those two capacitors in series looks like it's just then half. Now, if I then wanted to figure out, I have my battery and I have my C12, and then I have my C3, and I then want to turn this into a single capacitor, which I would call C sub 1, 2, 3. I again have two capacitors in series, so I can merge them together with the same formula. So then it looks like C sub 1, 2, 3 is equal to 1 over C12 plus 1 over C3. Before I plug in numbers, let's just show an example of this kind of general formula I have. I said that 1 over C sub 1, 2 is the same thing as 1 over C1 plus 1 over C2. So note that this is also the same thing as 1 over C1 plus 1 over C2. That's the C sub 1, 2, and then the 1 over C sub 3. So indeed, it looks like that general formula is holding, right? If I wanted to go from all three capacitors to one right away, I could just do 1 over C1 plus 1 over C2 plus 1 over C3, and then that is equal to 1 over C1, 2, 3. So then I can then calculate, making sure I flip things correctly at the end of the day. I'll just do it. 1 over, we said C sub 1, 2 is 5 microfarads, and then C13 was, what did I say, 100 microfarads. It's supposed to be a 5. It looks like a 6. So in this case, I could get a common denominator if I multiply the left one by 20 on the top and the bottom. So then this looks like it's 20 over 100 microfarads plus 1 over 100 microfarads equals 21 divided by 100 microfarads. So then if I flip it, 1, 2, 3, looks like it's 100 microfarads divided by 21, or 100 divided by 21, I get, it should be greater than 4, because 25 would be 4. And then 20 would be 5, so this ends up being 4.76 microfarads. So, which I ran out of room on this page, so I'll just redraw. So then what this says is, I have a battery that has 3 capacitors That is the same thing as that single same battery with a single capacitor that has a capacitance of equal to 123, which we said was 4.76 microfarads. And this was, we said, what was a 9-volt battery. So then this is 9 volts. So with this very simple circuit, one capacitor, one battery, right, I know that we've talked about to death that the potential difference across the battery is 9 volts. So then the potential difference across the capacitor better be 9 volts. So then if Q equals C123 times V battery, that then says that the charge that builds up on this equivalent capacitor seems like it is 4.29 times 10 to the minus 5 coulombs. Now there is no capacitor that has this capacitance, right? The original circuit, the circuit sitting in front of you on a lab table, had 3 capacitors. 2 of them had 10 microfarads, and one of them had 100 microfarads. So then you could ask, is this number I just calculated for the charge meaningful at all? Well, yes, because the rule with capacitors in series is that they build up the same charge on each. And just like if we go back a page to when we had a box versus when we opened the box, in this case, we can calculate the amount of charge that must build up on this side of the box versus this side of the box. But then that implied that the charge here was the same as the charge here, which we then argued then implied the charge here and here were also the same. So in this case, this is the charge that's built up, Q built up on each capacitor. That's actually in the circuit. And then what about the potential differences? Those cannot be the same, right? You can't have, if you have a 9-volt difference across the battery, you can't have 3 9-volt differences across the 3 actual capacitors, because we argued above that the potentials add when you have capacitors in series. So if there's only a 9-volt difference across the box, then there only can be a 9-volt difference across, in this case, 2 capacitors. So for our problem, there's only a 9-volt difference across the battery. You can imagine this being the box. There can only be a 9-volt difference across all 3 capacitors. But if we know Q and we know the original capacitances, that's not too hard to show. Because again, if Q equals C capacitance 1 times V1, the same charge equals C2 times V2, and the same charge equals C3 times V3. And I know C1, 2, and 3. You can show that V1 is about 4.29 volts, V2 is about 4.29 volts, and V3 is about 0.42 volts. And notice that V1 plus V2 plus V3 is 9 volts, as must be the case. Again, the 3 capacitors inside the equivalency brand box. This indeed meshes with what we should expect, as if it were just one big old capacitor. Okay. Let's do another one. So I have a battery, and it connects to another equivalency brand box. But then when I open it up, what do I find? I have a battery. Here's the box. inside the box. Instead, you have some sort of junction in the wire where the wire splits and it goes to two potentially different capacitors. The wires then merge back together and then leave the box. So this is then a case of capacitors in parallel. And we have to deal now with this idea of charge splitting. Now, of course, I can't take an electron and split it in half. But you can imagine many different electrons or many different charges, and then once they get to this junction, deciding to go one way or another. Like cars on a road. When the road divides, they have to pick one. They have to commit to one. So again, you have some charge that's moving. Conventionally, it's some sort of positive charge. And then once it gets to the junction, again, let me get rid of the box. It's not quite as messy. Once it gets to the junction, you might have Q1 go this way, and Q2 go this way. Now, charge is also conserved. So we have kind of the junction rule, which really is just conservation of charge, such that the charge that goes in must equal the charge that comes out of the junction. Or in this case, that Q equals Q1 plus Q2. Whatever charge goes in, those electrons have to pick a road. And then if I were to count the electrons that went through both roads, that better match the same amount. That better be the same amount as what came in. And then similarly, there's another junction here, but again, that should be that Q1 and Q2 better merge back together and get Q. So it doesn't tell us any new information, but sometimes you'll have multiple junctions and they will each be telling you something different, depending on what's going on with the currents, which we are heading towards. So there's some V battery, and then there's some capacitor on the left, which I'll say has some potential V1. There's some capacitor on the right that has some potential difference V2. There might be different amounts of charge that's building up on those plates. Now we got to think about what is the same and what is different. Because notice the thing for charge is already a little different. Before we said all the charges were the same. Now it seems like the charges are kind of adding together. Before we also said that the potentials added together. Now we're actually going to see that the potentials in this case are the same. In a sense, this is flipped from the series case. So if I draw equipotentials, the top terminal then connects to this wire, which then divides and touches two different plates. So that is all one equipotential surface. Similarly, the bottom plate connects via wire to the two bottom plates of the capacitors. So that is all one equipotential surface. So notice just by the colors, show that the potential across the battery, blue to red, is the same as the potential across the left capacitor, blue to red, is the same across the right capacitor, blue to red. So in this case, all the potentials are the same. So indeed, this is kind of flipped from the series case. Just as an aside. In the series case, all the charges were the same and the potentials added. Here, the charges add, all the potentials are the same. Again, I did not declare or define that in any way. We argued that through physics. So, with the same kind of goal in mind, this left side with the box, which again, the box claimed there was a single capacitor in the box. So we should have some relationship between charge, this equivalent capacitance, and the potential across the battery. And so across the box, Q box, my subscripts are too small. So for the box, we at least know we should get Q across the box is equal to C equivalent times V battery. How does that then apply to when we open the box and actually there are two capacitors in parallel? Well, then, of course, we can do the same sort of thing that we did before. Q box, what goes into the top of the box and leaves the right of the box. Since there is that junction, we know that that better equal Q1 plus Q2. I know I'm switching between uppercase and lowercase, but that's fine. So then Q box, we said it was C equivalency, V battery. Then that equals the left capacitor multiplied by the potential across it, and then the right capacitance for the right capacitor times the potential across it. So this is definition. But then we also said that V battery equals V1 equals V2. So I can divide them out and I get that C equivalent is C1 plus C2. And this is when they are in parallel. Capacitors in parallel. Which is much simpler than the. It's not 1 over C equivalent. You just add them together. They have their effective capacitance is just the sum of the two. So if we were to summarize, we have series, and we have parallel. We have, of course, formulas, which are nice. It's usually good to remember how we got them. And I'll write down the general formulas, right? So it's not just C1 plus C2, right? This also generalizes that if you have 3 or 4 capacitors in parallel, say, you just add them all up. Similarly, in series, 1 over C equivalent is then the sum of 1 over all the individual capacitors. For series, we said that the charge is the same. And here, we said that potential is the same on each. And then for series, we said that the potential added, series activated, go away series. And then in here, the charge adds. I'll say adds, really, it's right. It's the idea of the it's junction, it's charge conservation. So then the trick is that when you have more complicated looking circuits, like suppose I have a battery that goes and hooks up to a capacitor, which then after that capacitor goes down and there's a capacitor here, then there's another capacitor here, and then those come and merge here, and then go back to the battery. Oops. Which of these are in parallel? Which of these are in series? Again, notice that none of them are drawn actually in parallel. But again, the word parallel doesn't mean they actually have to be literally side by side with one another. The idea with parallel is that they have the same potential difference across them. So if I were to draw, again, using some colors, the top of the battery then is this equipotential. The bottom of the battery is this equipotential. And then there's this intermediate one in the middle. If I look, this capacitor and this capacitor are in parallel with one another because they have the same potential difference across them. So then I could use my formulas and rules and calculate an equivalent capacitance for them. And then that would be replaced with some equivalent capacitor, which then would simplify my circuit to this. So again, if I give some numbers, if this is C1, C2, and C3, and this is still C1, and then this is C23. After we use the appropriate formula. In this case, we would just add them together. It would just be C2 plus C3. That's the formula for when they're in parallel. But then, this is then easy to see that these two are indeed in series with one another. And I could then replace them with a single capacitor with some equivalent capacitance in the same way, but different formula in this case. And then as I disentangle them to find, the charges and the potentials across them, I have to just remember the rules of which of for series and parallel, which is the charge the same, and then which is the potential the same. All right. I'm already at an hour and 10 minutes. But, oh well. Let's talk about a kind of actual practical application of capacitors. There's lots of applications of capacitors. I showed many examples of what capacitors look like in the previous lecture, particularly on computer chips. There's capacitors all over the place, for storing and then discharging energy, and they can be fine-tuned in terms of the energy they store and then the rate at which they can discharge. Again, we haven't said anything about the time dependence of these things because we need to do resistors before we can do that. So we're building towards that. That'll be after the break. But let's talk about just, capacitors and batteries are very similar in that they are kind of means of storing energy. Though again, I would think of a battery more as a way of kind of driving current. Though again, capacitors are essentially doing the same thing in that they're storing energy and then driving that energy in some way by making charges move. Now, let's talk about electric cars, where you have some sort of electric, essentially, with these rechargeable batteries. Essentially, they're just capacitors, things that can store things up and then discharge, and then you can charge them up again, and then that energy can be discharged. So you can essentially think of electric car batteries as just a big old capacitor. Now, of course, we are working towards more efficient electric cars, more efficient, and there are still a lot of technological challenges that we have in terms of the amount of energy a particular car battery can store, which then translates into the amount of work it can do, how far that car can get before it has to be charged up again. Charging stations also still have a ways to go, and that it still takes kind of a long time, even at like Tesla supercharging stations. It's like, 30 minutes or something like that to charge up the battery, which that's much longer than the time I spend at a gas station filling up my tank. 30 minutes is a long time to kind of hang out at a charging station. It's not hours, but nonetheless, we still would like to get that number down as well. Well, let me focus on the energy content of a battery. So just to give us some numbers to compare to, what does gasoline give us in terms of energy? So you can look these things up. Gasoline gives you roughly about 130, and I'm going to talk about energy densities here, 130 megajoules. Again, mega is 10 to the 6. Mega, million, 10 to the 6 megajoules per gallon, which ends up being about 34 megajoules per liter. And since a liter is 10 to the minus 3 meters cubed, that is the actual volume of a liter. Think of a 2-liter pop can, or not can, pop plastic bottle. Half of that, is roughly 1 meter times 1 meter times 1 meter. Or sorry, 10 to the 3, 10 to the minus 3, times 1 meter times 1 meter times 1 meter. So then this ends up being about essentially, if I divide by 10 to the 3, that's 34 times 10 to the 3 megajoules per meter cubed, or that's roughly about, not roughly, but 34 gigajoules per meter cubed. So just to give you a sense of the numbers, right? Because if we want electric cars to be, right, it's obviously greener and it's better for our environment that we work towards a renewable energy source. But the unfortunate reality of capitalism is that if economically it does not make sense for people to use these things, people won't. And companies will not kind of invest in designing electric cars, for example, if it's not really efficient and worth it, for their consumer base. Unfortunate reality of capitalism. That's why it took a long while. It took, when solar panels were first coming out, everyone kind of thought, okay, we should all just switch over to this renewable energy source. But in the 90s and the aughts, the efficiency of a particular solar panel was actually quite low, and that, even if it had, a perfectly sunny day, the amount of sunlight that actually got transferred into becoming usable in terms of work was very low compared to what you would get with traditional energy sources. So there was not a lot of impetus for people to go to solar charging or solar panels on, say, cars and buildings and whatnot. That has gotten much better in the last decade. So that consumer-wise, it's becoming more economically feasible to use that as an energy source. Again, I wish that were not the case, that we are driven by capitalism. But at the same time, if I want to try to think positively here, perhaps that has encouraged people that are working on these things to come up with more novel ideas to create more efficient solar panels. And the same thing has to now happen with car batteries, electric car batteries. So, now the base model, and I don't know if this is the same battery they use these days, but let's just use this because it gives me some simple numbers to work with. Kind of the base model, the base Tesla model. The battery is able to provide about 200 megajoules of energy before it needs to be recharged. So we'll use that as kind of a round number of, if we want to create an electric battery, right, this is kind of a number that we're going for. And then, of course, we want to make this number as high as possible. Because if I go back up to the gasoline, if I have 130 megajoules per gallon, and to use round numbers, suppose my car has a 10-gallon tank, that means that there's a total energy of about 1,300 megajoules in a full tank of gas. which obviously is almost a factor of 10 larger than what the Tesla battery is giving us. And of course, there are some things that electric batteries can do. When you brake, you can charge your battery by converting the energy that's dissipated by braking, and use it to charge your battery up. So you get a little bit more bang for your buck as you drive, but still, the goal is that we want to make this number, this 200 megajoules, as high as we can. But there's still even technological challenges to achieve this 200 megajoules. If you look, the battery of a Tesla car, right? It's a reasonable size battery. This big thing that's usually in the trunk or wherever they are. Lost my train of thought. But if we had a higher density of energy, or if we had a battery or a capacitor that had a higher energy density, then we might be able to cram the same amount of energy into a smaller volume, or we could take the batteries that we currently have and store more energy overall in that same volume. So let's just get a feel for some numbers. So we know that capacitors store energy. And the total energy we derived last time was 1/2 the capacitance times the potential difference squared. And then we also talked about the total energy is that the energy density, energy per volume, we then worked out was 1/2 epsilon naught, the square of the electric field. That is essentially storing that energy between, say, two plates, if you think of two plates. So the question is then, how big of an E field do we need to get, say, I'm going to stick with the original kind of number, 200 megajoules? And then what volume should we put that in? Well, there are other limitations you have to think about. We've done many problems where we've talked about where essentially, what happens when there's a lightning bolt or a spark. You're getting dielectric breakdown in air, where the air, if you have an electric field that's too strong, the air in between the two plates will become ionized, and you'll just get then, charge will then start flowing between the two plates, which is not what you want, because then the electric field will eventually, go away, because the charges will, the positive charges and the negative charges will find themselves again, which then will reduce the electric field. So we know that E for air, the electric field of when breakdown occurs, we said it was about 3 times 10 to the 6 newtons per coulomb, or 3 times 10 to the 6 volts per meter. 10 to the 6, again, mega, so it's about 3 megavolts per meter for that electric field. So if I just use that number, U of 1/2 epsilon naught, if I have a capacitor battery that is, two plates with just air in between them, I know I can't make the electric field too big. So let's say I can get it up to, but not exceeding this breakdown limit. That only gets me an energy density of about 40 joules per meter cubed. So to get 200 megajoules, which I might write as 40 joules per meter cubed, and then I can imagine, I'll take my battery, I'll simplify my battery and just assume it's a cube. So it's some L cube, right? So the volume of that battery then is L times L times L, if it has some length L. That then requires an L that is about, when I work this out, about 170 meters. Again, a meter is about a yard, which is about 3 feet, right? So this is a battery that is the size of a small hill. And I'm not seeing Tesla cars drive around the road with small hills in their trunks. So clearly this is not how it works. So how do we get around this? Well, the idea here is that if we could put something in between the plates, such that that material has a higher threshold before it starts to become ionized, you could then get a stronger electric field existing between the two plates, which then turns into a higher energy density, which means more energy can be stored in that volume. So again, if I just use two plates as the example, and then if I were to say, fill it with some material, fill it with some sort of material. So a material that can allow for a larger electric E field before breakdown. Then maybe that works. Because again, the volume density is proportional to E squared. So if I can get an electric field that can be 10 times larger, E squared then becomes 100 times larger. So you get more bang for your buck if I can make the electric field as large as possible. So for example, you might use something like diamond. So for diamond, the breakdown is not 3 megavolts per meter, but it's something more like 2,000 megavolts per meter. Again, almost about a factor of 1,000 larger. Or 10 to the 3 times larger, which then means E squared is closer to 10 to the 6 times larger. It's 10 cubed, and you square the entire thing, which then results in an energy density of not 40 joules per meter cubed, but about 17 megajoules per meter cubed. Now, it's not quite, that's better, but then this requires a volume. Again, if I want to get that original Tesla battery, that requires a volume of about 2.3 meters cubed. So again, a capacitor that's, a little, maybe 7 feet by 7 feet by 7 feet. Still not super practical in this case, but we're getting closer. And then also notice it's still really not coming anywhere. 17 megajoules per meter cubed is really not coming anywhere close to gasoline, which is 34 gigajoules per meter cubed. So the thing we have to then bring into here is that something actually very interesting happens when you have a material that's not just a vacuum. We always kind of treat air and vacuum as the same. But then in many cases they do behave very similarly. But when you have something like diamond or some sort of solid, which has a lattice of nuclei and electrons that are being shared around, something actually very worthwhile and interesting happens. And so let's go back to our simple picture of an atom. So an atom has a nucleus, and then the electrons roam around as some electron cloud around the nucleus. So again, if I have some electron cloud, and then I have some nucleus that's in the center, there are positive charges in the nucleus, and then there are electrons that roam around in this electron cloud surrounding it. In the presence of an E field, high school presence. That's my eraser system. So inside an E field, suppose we have an E field that points downward, like the E field in between these two plates. The positive nucleus wants to go in the direction of the E field, where the negative electrons have feel a force that pulls them up in the opposite direction of the E field. So what happens is the electric, or the nucleus and the electric field kind of become lopsided, and then you end up getting the positive nucleus down here with the negative electron cloud kind of sloshed over to the other side. So in this case, the atom looks kind of like a dipole. Which we've also talked about in class before. Now, some molecules have this naturally, like the chem majors in the class, are very familiar with the polarity or polarization of the water molecule. But essentially, in the presence of an electric field, even individual atoms can become polarized in this sense. And so then what happens is, if I go back to my two plates, and it's filled with some material. I used blue before. I realized that was probably a mistake. It's too dark. So I'll have it. It's filled with some material. And of course, we can't see individual atoms, but I'll draw just a couple of them. Nice if I could have drawn four. Add a fourth one. Nope, that failed. All right, let me try again. So here's the plate, and I want to draw at least four atoms to demonstrate this. And then here's the other plate, and they are filled with, right, there's some material that's in between them. And again, the plates have positive charge here, and negative charge here. And so as a result of the two plates, there's an electric field that points down. So again, that's the electric field due to the plates. And so then naturally, the atoms that make up this material, this diamond or whatever was in there, start to align themselves such that the positives want to go down and the negatives want to go up, so that each of these have plus and a minus that orient themselves with the pluses down and the minuses on top. And so, since these atoms are so small and close to one another, there is a lot of cancellation that occurs. So if you notice, let me use the highlighter. Let me actually just zoom in. Right, these two essentially cancel one another. These two cancel one another. These two cancel one another. But then there's this plus that's left over and this minus that's left over that doesn't have a companion to cancel it out. Essentially, then this inner section here, all of those essentially end up canceling each other out. But then there's this thin little surface layer where you have a bunch of negatives aligned up top, a bunch of positives that are aligned on the bottom. And so as a result, that creates an electric field, but points in the other direction. There's an electric field from dipole material. that then ends up forming in between the two plates. And so overall, that means the net electric field, so the dipole creates an opposing electric field. So then the net electric field, which is the sum of the two, is reduced versus the electric field when they're, with a vacuum or when it was just air or whatnot. Again, this could still happen with air too, but we'll compare it to, say, air or vacuum. So the overall electric field gets reduced. Now, that doesn't seem like it's working in the right direction. We want to make the electric field as strong as possible. But that electric field was formed from charges building up on the two plates. Charge was, a battery pumped charge to build up on the plates, which then created that electric field, which is then, where the energy was being stored. So then imagine if you keep this thing connected to a battery while you're charging. So imagine then connecting back to a battery. So if I then connect this back to a battery, which has some V battery that it's trying to maintain across the two plates. Now, without any material between the two plates, right, some electric field was established, right, the kind of one I wrote in black, the electric field from the plates. But because of this material that's in between the two plates, it created an opposing electric field, which for that given amount of charge, again, let's just use round numbers, suppose 1 coulomb of charge was moved to the top plate, so there's 1 coulomb of negative charge on the bottom plate. That created a particular electric field. But then because of these dipole interactions, that 1 coulomb of charge, the net electric field ends up being reduced because there's that opposing electric field that I've drawn in green. So if that electric field, since E net does not have a potential difference equal to the battery, because again, the net electric field is reduced, the battery drives more charge to the plates. In order to get that delta V back, right, because the dipoles have kind of denuded the potential across the plates because the electric field has gotten weaker. So then the battery starts to then push more charge towards the plates, and as a result, more charge builds up, and the electric field is pumped back up again. So what does this mean in terms of energy storage? Well, I know for the capacitor, the amount of charge that builds up on it is equal to its capacitance times the potential across the plates. Now, again, we have the capacitor connected to a battery, so it is trying to maintain a potential that is the same as what it was before, V battery. That has not changed. If it's 120 volts, right, it tries to bring that potential back up to 120 volts. But it did so by having to pump more charge than it did as if, if there was just air or a vacuum in between, it had to pump more charge onto the plates than it had to in the previous case. Again, how do we get the two sides of this equation to match? That means the capacitance has to increase as a result. So driving Q to return to V battery this has the effective result of the capacitance increases for the capacitor. And we can write this as, we can say that the capacitance ends up being some constant kappa times what the capacitance was for air. So I should say capacitance increases beyond its value for the vacuum. If it was just a vacuum between the two plates, or air, since the dielectric constant for air is essentially the same. I have it here in my book. Yeah, if a vacuum has a, well, let me just say. So it has an effective result of driving up the capacitance versus what it is for, say, a vacuum or air. Where again, the idea of that kappa is 1 for a vacuum. And then again, I'm treating air to be the same, though they're technically not. Kappa is 1, if kappa is 1 for a vacuum, kappa is 1.00054 for air at normal atmospheric pressures. So again, let's just call that 1. So the vacuum and air more or less behave the same. But then kappa for, say, if I had paper in between the two plates, kappa is 3.5. The capacitance is 3.5 times larger than if it was just empty space in between and I replaced it with paper. Or for silicon, it's about 12. For water, it's about 80. So I guess it depends on how, there's a temperature dependence with water. For diamond, we saw it could be much, it could be much larger. So this idea here is that when you replace the material in between the plates with some other material, you can get, and this is what's called the dielectric constant. Dielectric. I think I actually called epsilon not the dielectric constant last time. I did not mean that, though they are connected. So if you replace between the two plates of the capacitor with some other material, you can effectively increase the capacitance of that capacitor. And again, why is that helpful? Because if we have the total energy in a capacitor, we said was 1/2 the capacitance times the potential difference squared, well then that becomes 1/2 kappa times the capacitance when it's air times the potential difference squared. So if I can make kappa really large, I can get an overall energy that is overall larger, which then, since the energy density is just U divided by volume, that then also means I can get a larger energy density as a result. And so there are new novel materials that are being developed in labs. There's a lot of work going up, happening up in Canada. That's being led under, sorry, I'm blanking on his name, but one of the scientists that was essentially responsible for the development of the lithium-ion battery. They're doing a lot of work to come up with some novel materials that have very, very large values of kappa, because if they can do that, then they can essentially drive very strong electric fields in between these capacitors plates and store a lot of energy in the electric field and do it in a small volume. So they've claimed, and again, this is only in experiments, claims that they've gotten to values of kappa exceeding something like 10,000. So you can imagine that if we were to take, say, the results we had for diamond and upgrade it and say that what if we were able to take what we have for diamond up above and make and use a value of kappa that is 10,000, so increasing it 10,000 times beyond that. This then gives us some numbers. So if we take diamond and upgrade, with these sorts of numbers, upgrade. That then ends up getting us energy densities of about 170,000 megajoules per meter cubed. So that if you wanted to get, which notice is 170 gigajoules per meter cubed, which exceeds what we had for gasoline. Right, this would make this even better than gasoline. Right, we said gasoline was about 34 gigajoules per meter cubed, versus now this would be something like 170 gigajoules per meter cubed. This also means, I don't want to go to a new page, this also means to get, again, if we wanted to go back to our original battery of, we want a battery with 100 megajoules, or 200 megajoules rather, that then only requires a volume of about 1 liter. So you have, something that's half a pop bottle. That 1 liter container could contain as much energy as kind of a base model Tesla battery. So then you can imagine it's okay. I can imagine it's okay to want to have a couple of those, right, to make my overall battery. Then I can have an overall battery that can actually get me somewhere on a single charge. Or again, thinking of it in terms of here, since this exceeds what we have for gasoline, you could think of, what a common tank of gas, the size of a common tank of gas in a car today, if you were to replace that, with a battery that takes up the same volume, you can get way, way farther on a single charge compared to gasoline, which, of course, is what we are ultimately aiming for, because then that would effectively mean that we could rule out the need to ever use gasoline. Of course, this does not get us around the charging aspect, which is also kind of still in the works and people are thinking about it. But I thought it was kind of a fun example to show kind of a practical use of capacitors and how there's still a lot of work going on today to think these things through.